civilpe.net.
All right, we're going to revisit our rectangular concrete section once more. Now this time we're going to go the other way with it. Instead of checking minimum steel, we're going to go to the realm of maximum steel for a given section. Now, one quick note, an over-reinforced concrete section typically means a beam that has steel that has not gone into yielding at failure. So basically the strain in the steel does not reach that 0.00207 for grade 60 steel when it reaches failure. A beam with steel like that does not satisfy ACI requirements, so in this case that just means that this section is not going to be tension controlled, or the strain in our steel is not going to reach that 0.005 limit for a tension controlled section. So we've got our 12-inch wide by 24-inch deep beam. Now the difference with this beam and the other two is our bottom reinforcement for this beam is now going to be number 8 bars in 2 layers. The 2 layers, the clear spacing between the layers is per ACI 1 inch. So just keep that in mind, that that's going to be 1 inch clear spacing. That's industry standard. So we've got a concrete section with concrete strength of 60 or 6,000 psi. The yield stress of our steel is 60 ksi, and what we want to do is determine the nominal moment capacity of this section. Now our assumptions are going to be exactly the same. Plane sections remain plane. The concrete strain at the extreme compression fiber is 0.003. The tensile strength of concrete is completely neglected, and once again we're going to ignore the steel in the compression zone. So we're going to ignore those 2 number 4s to simplify our calculations. So let's go back and develop our stress and strain diagrams once again. So here's our strain diagram. You'll notice I have 2 different strains depicted on this diagram. The first strain, strain sub T, or epsilon sub T, that's the strain in the steel at the extreme tensile layer of steel. The second strain, epsilon sub S, is our strain in the steel at the centroid of this entire group of steel at this bottom. Now why do I designate or distinguish between the 2 of those? Epsilon sub T is used to determine if the section is tension controlled. Per ACI, you need to check the strain in the steel at the extreme layer of steel in tension and determine if that is great and the strain in that layer of steel is greater than 0.005. Now when we check whether or not the strain in our steel goes beyond yielding, we want to check that at the centroid of the group of our steel, or epsilon sub S. ACI denotes the distance from the extreme compression fiber to the extreme layer of steel is D sub T, and the distance from our extreme compression fiber to the centroid of our group of steel as D. C, once again, is the depth from our extreme compression fiber to the neutral axis of our beam section. Now we've got the stress diagram. Looks very familiar. We've got our compression force. It's acting over a depth A, which is the depth of our Whitney stress block, and it's acting over the entire width of our beam. And we've got our tension force, which is equal to the area of steel on our bottom layer, or the area of the group of steel at the bottom of our beam, so all number 8 bars, times the stress in that steel. So first, let's calculate D. And D is going to look a little bit different. Now D is going to be the overall height of our beam minus the clear spacing, minus the diameter of the stirrup, minus the diameter of that bottom layer of reinforcement, minus the clear spacing between the bars divided by 2. So we're calculating the depth from extreme compression fiber to the centroid of this entire group, which is that level right there. So if we calculate that out, we get that D is 20.5 inches. So now we want to use equilibrium once again to solve for A, the depth of that Whitney stress block. So bring up our stress diagram once more. From the rules of equilibrium, like we've said before, we know that the compression force must equal the tension force. So C equals T. From per ACI, with their approximation using the Whitney stress block, we know the compression force is equal to 0.85 times F prime C times the width of the beam times A, the depth of the Whitney stress block. So substitute our values in and we get that our compression force is equal to 61,200 pounds per inch times the depth of that stress block A. our tensile force is equal to the stress in the steel times the area of the steel. Once again, we're going to assume that that steel yields, and we'll later confirm this. So our tension force is going to equal 60,000 psi times 8 number 8 bars, or 8 times 0.79 inches squared, and we get a total of 379,200 pounds. So now we use that to solve for A, and we calculate that A is equal to 6.196 inches. Using our strain diagram, we need to figure out the strain in the steel at the extreme tensile extreme layer of steel, so epsilon sub t. But first we need to figure out what C is using the relationship from ACI, that A is equal to beta 1 times C, where beta 1 is that factor that relates the depth of the Whitney stress block to the depth of the neutral axis based on the concrete strength. So for our 6,000 psi concrete, we come out with a beta is equal to 0.75 and C is equal to 8.261 inches. Now let's calculate the strain in that extreme tensile steel using similar triangles. First, we need to calculate the depth from the extreme compression fiber to the extreme layer of steel. Now that depth is equal to 24 inches, which is the overall height minus the clear spacing, minus the diameter of the stirrup, minus the diameter of the bottom layer of steel, the number 8 bars, which is 1 inch, divided by 2. So that gives you 21.5 inches from the extreme compression fiber to the center of that bottom layer of steel. Now using similar triangles, we can figure out that C divided by 0.003 is equal to D sub T divided by 0.003 plus epsilon sub T. We rearrange to solve for epsilon sub T, substitute in our values, and we get that epsilon sub T is equal to 0.0048. Now what does this tell us? We need to determine if our section is tension controlled. Now, a section is deemed tension controlled if the strain in the extreme layer of steel is greater than 0.005. Unfortunately, we only have 0.0048. So what does that mean? Per ACI section 10.3.5, epsilon sub T at nominal strength for flexural members shall not be less than 0.004. So 0.0048 is greater than that, meaning this is acceptable. But we're going to have to adjust our phi factor because our strain is less than 0.005. So the strain for our section is between the limit for compression controlled, which is 0.002 per ACI section 10.3.3, and that 0.002 is for a yield stress of 60 ksi. If your yield stress changes, you're going to have to calculate what that compression controlled limit is, and the limit for the tension controlled sections of 0.005. Therefore, we must interpolate to determine our phi factor in accordance with ACI 9.3.2.2. So to interpolate, we get 0.9 minus 0.65 divided by 0.005 minus 0.002, where 0.9 is the phi factor for the tension controlled region, or tension controlled section, and 0.65 is the phi factor for a compression controlled section. 0.005 is the strain limit for a tension controlled section, and 0.002 is the strain limit for a compression controlled section. And we set that equal to R value phi minus 0.65 divided by R value 0.0048 minus 0.002, and then we solve for phi, and we come up with our phi is equal to 0.88. So because we are not tension controlled, we couldn't take that phi of 0.09. We actually had to reduce it a little bit. So now we need to determine the strain at which steel yields and check our assumption that our steel in fact yielded. Like we did previously, using Young's modulus, we figure out the strain at which our steel yields, and we'll come up with that strain of 0.00207. Now, when we checked that the section was tension controlled, we checked the strain at the extreme layer of steel, but when we're checking to see if the steel yields, we're checking it at the strain at the centroid of the tensile steel. So epsilon sub s is what we need to calculate. And from similar triangles, once again, we know that epsilon sub s equals d times epsilon sub c, all of that divided by c, minus epsilon sub c. So that's equal to 20.5 inches, our d, which is our distance from our extreme compression fiber to the center of our group of steel, times 0.003, which is the strain in our extreme compression fiber, divided by 8.261 inches, which is our calculated C, minus 0.003, and we figure out our epsilon sub s, disregard this t, it should be epsilon sub s, is equal to 0.0044, which is greater than 0.00207. So our assumptions are correct, and the steel does yield, and we don't need to change our calculations. So now let's determine if the beam section satisfies the minimum steel requirements of ACI. Now, if you went through the last example, you know that this beam section is going to satisfy our minimum steel requirements, but I want to do it one more time just to kind of get that into the memorized portion of your brain, into your long-term memory. So per ACI section 10.5.1, the minimum steel requirement is AS min equals 3 root F prime C divided by F sub Y times the width of your web times the depth. Now that depth is from the extreme compression fiber to the center of your group of steel. And that has to be greater than or equal to 200 over F sub Y times BWD. So for us, we substitute in our values, and we get our A sub S min has to be greater than 0.95 inches squared. Now, we have 6.32 inches squared, which is way greater than that 0.95 inches squared, so therefore we satisfy these minimum steel requirements. So now let's finally calculate the nominal moment capacity of our section. So using moment equilibrium, we're going to calculate the moment capacity by taking the moments about the center of our tensile force or the center of our compressive force. Now I like to take it about the center of my compressive force most of the time if you have a rectangular beam like this, just because it's a much easier calculation. So we'll calculate about the center of our compressive force. So we know that phi mn is going to equal phi times our tensile force times its moment arm, which is going to be d minus a over 2. So phi is 0.88 as we previously calculated. Our tension force is the area of steel times F sub y. So phi mn is equal to 0.88 times our area of steel, which is 6.32 inches squared, times F sub y, which is 60 ksi, times d, which is the depth from the extreme compression fiber to the center of our group of steel, or 20.5 inches, minus a over 2. And a we calculated as 6.196 inches. And we come up with a moment capacity for this section of 5,807 kip inches, which is equal to 483.9 kip feet. So now if you have any questions or comments, please send me an email at info@civilpe.net. For more information, more videos, more help, check us out on the web at www.civilpe.net.